on the other side, so the current's going to come out of here into there, right? And then it's going to go all the way through this, and on this side I've got another plug here, yeah? There we go. And then I'm going to take a light bulb and plug it in there. Yeah? I know, this is pretty cool, right? And now the current is going to get to the light bulb, right? So let's turn this on and see what happens here. Oh, it is on. Okay, we've got to turn up the voltage. Is the light bulb lighting up? No. Yeah, well, okay, what probably happened here was some charge. Actually, this is now at like, I don't know, 20 volts, right? So it's sort of a little bit of charge kind of flowed onto that thing. Why is it not flowing through this thing? Why isn't it just sort of spraying off into the room? Is it possible that it just doesn't have enough voltage? It would take tens of thousands of volts to make charge sort of go off into the room, wouldn't it? Right? So at this voltage, what I need to do is I need to, let's turn that voltage down there, right? What I need to do is actually let it go back to the power source, don't I? So I got to make a return path here, so it can just sort of pump it along. Okay. Now we ought to be able to light up our resistor. Let's put this like here. Okay. Let's turn this up. Can I light that up there? It's lighting up. Okay. Why does it need a return path? Because it doesn't have, there's not enough voltage to make it just spray off into the air, right? That would take tens of thousands of volts. We did that with a Van de Graaff, didn't we? We made sparks jump like that, right? And besides, that would be kind of dangerous, right? Be like, and then when it did flow, it'd like blow this light bulb up and stuff like that, right? Okay. But here, if we've got a return path, this thing is like at 0 volts, and the current can just flow along the wire, and it's got a place to flow. So it's like a little pump, right? It's got an input, it's got an output. It's coming out of this red. It's going through a resistor. It's going through the light bulb. Then it's got to go back. Yeah? Yeah.
Where else can you move the resistor from?
Ah, there we go, right? So there's two things we can change, right? There's two things I can change about this. I can change the resistance, and if I increase the resistance, that is, I make it go through more, watch the brightness of the bulb. Now the resistance is more. What's true about the current? Less current, yeah? If I make the resistance less, we get more current. So resistance is resistance to the current, yes? Okay? And so low resistances cause high currents. High resistances cause low currents, okay? Voltage is like pressure. So if I turn this knob, if I turn the pressure down, what happens to the current? Current goes down. If I turn the pressure up, the current goes up. There we go. Yeah, it's just like that, right? It's just like a hose here. So I like to write Ohm's law. Ohm's law, strictly speaking, is written the way it's given to you up there. But I like to write Ohm's law, and this is kind of a forbidden way of writing it, you know? Okay? I like to write it in terms of current. I is V over R, right? But it's also equally true to say that R is V over I, or V is IR, right? Or you could do the triangle. This is the Boy Scout way, right? I, R, V. Cover up the thing you need. I is V over R is V over I, V is IR. Yeah? But I think I already showed you that, right? I don't want to make any more stupid jokes and raise your ire. Okay, so take a look at this. Take a look at this again. Okay, this thing here, this is voltage. Voltage is like the pressure, right? Resistance is like, in a water pipe, is like one of those water pipes that's corroded and there's only really a very narrow channel. So resistance is like resistance or constriction or something like that, right? Okay? Right? And then this is our current, and that's like a flow rate. So look at this formula. Look at this formula. Okay, and we're looking at the current. The current is, you can tell good that it's a big current because the light bulb is bright. The brighter the light bulb, the more the current. Yes? Okay, so let's look at the light bulb. Look at that formula. If I increase the resistance, what should happen to the current? If I increase the resistance to current, what should happen to the current? It should get less, correct? If R gets bigger, I gets smaller, correct? Okay, so let's increase this. I'm going to increase the resistance. It's like, whoops, you can't see it. Here we go. I'm increasing resistance, increasing. If I decrease resistance, current gets bigger, it gets brighter, right? And then if we just keep it like that, if I increase the numerator, the voltage, it should get brighter, and if I decrease the numerator, it should get dimmer, right? Yeah, these burn out. They're like 6-volt lights. So they're a little applause for the... Pass around. Okay, and then I'll pass this box around. This box has, there are things, oftentimes in a circuit we don't want an infinite amount of current flowing. It's very rare that we do, and then even then it's like impossible. Okay, and so oftentimes we need to limit the current in a circuit, a lot of times, almost always. Okay, so if you look at little circuit boards, you will see, and I'll pass this around, you'll see resistors. These are things that are designed to limit current. Okay, that is their role, and they're ubiquitous. Okay, the size of the resistor is not its resistance. Okay, the size of the resistor is actually its power handling capability. This one I think is like 1/4 of a watt. These ones can, and the big power ones, the ones that look fancy, this one can dissipate 20 watts. That's kind of a lot. Okay, these ones actually look like this resistor, only they've painted them with something, and I can no longer read the writing on it because I'm old. Okay, and then here are some small resistors. The smallest little bitty resistor in here might actually be 1,000,000 ohms. Might have a lot of resistance. It just doesn't handle much power. Okay, so I'll pass that around. One of them has a little screw on it. What do you suppose that's? You suppose it's a variable resistor? Yeah, these are called pots. They're called potentiometers. Okay, and then one of the resistors is just a wire that we made. It's nichrome wire. And it looks the way it looks because we've made it glow red hot at some point. You can pass that around. And then the resistors, the little cylindrical resistors, okay, have a color code that you have to look up. Okay, and the way it works is it's like scientific notation. Okay, so it's the first one is the first digit. Our first digit here is a 2. The next digit here is a 5, right? And then the yellow there is the times 10 to the, so it's 25 times 10 to the yellow. Where's yellow? 4, right? Okay, so when you write this number down, it's 25, and then 1, 2, 3, 4 zeros like that. So it's actually 250,000 ohms. It's like that, yeah? And what? No, you don't need to write it down. I'm just saying this is it. It's in your textbook, right? And then the mnemonic device for this is, I can't think of a better one, okay? Oh, good thing I got the microphone working again. Okay. No. Okay.
Did you say victory?
Victory Garden Walls.
Victory Garden Walls.
All right, class. Please come up with a better one. I think it's like you hear it once and it's burned into your memory. Okay. Okay. So this is a circuit here. There's a 12-volt battery. On the battery, the big side is the plus side. That's easy to remember, isn't it? Yeah. Okay, current goes from plus to minus. This is an ammeter here. It measures current. And then ignore the fact that the circuit is broken, like right there, And this is 120 milliamps. So the question is, what's the resistance in the circuit above? And so resistance is going to be V over I, right? So it's 12 volts divided by 0.120 amps, right? 120 milliamps is 0.120 amps, right? And 12 divided by 1/10 of 12